For the next example problem, we'll be working on this corridor, Dumfries Road, and we are going to model this intersection located on the east side. And what we want to do first, we want to analyze this intersection using a single period analysis approach. We have the volumes here, the PKR factor, and we know this is an actuated coordinated intersection. For the first part, we want to enter these inputs, which will include the intersection geometry, the lane configurations, certain traffic and geometry related inputs. So with that, let's get started and let's open the HCS streets module. We can start a new intersection. And most important, we want to make sure that we set the forward direction correctly to match the major street. So this intersection will be an east-west major street, so you can pick whatever works better, eastbound or westbound, but make sure you don't select northbound or southbound because this will set the forward direction to north-south, and that, of course, is not something we can change later. So let's keep eastbound, and let's hit OK. And first, let's get started by entering our PKR factor on the top left corner. So this is 0.96. Let's also model our lane configurations in my intersection. You can do that by clicking the arrows. For example, the eastbound approach, we have 3 through lanes. So let's click it once, twice, and then this should match what we have for our eastbound approach. For my westbound approach, I have an exclusive left. I have 2 exclusive through lanes, so I need to add 1 extra. And I need to replace my exclusive right. So I'm going to click inside the intersection. And I want to replace that with a shared through right, as you can see over here. For my southbound approach, I want to replace my exclusive right and my through with a shared through right movement. And on the northbound approach, I have 1 exclusive left. I have a shared through left lane, and I have an exclusive right. Next, let's start entering our demand volumes for each one of our turning movements. So eastbound left, 25, eastbound through 2040, eastbound right, 400, eastbound left, 200, 1685, 32. For northbound, I have 100 left, 8 through, 200 right. For southbound, I have 75 left, 35 through, 80 right. I have 12 feet lanes in all approaches. Let's enter our stored lengths. This can be measured on the map, and whatever I enter here will be compared against my computed queue lengths. So I can get my queue storage ratios, and I can check for the presence of queue spillbacks. You'll notice that shared lanes, they may be disabled because the inputs are not necessary here. So whatever I enter for the through movement will be applicable to the shared right turn movement. Let's keep the base saturation flow rate 1900. Let's enter 2% heavy vehicles in all movements. And finally, let's set our speed limits. We also don't have to worry about grade, everything is 0. For eastbound, I have approach speed of 45 miles per hour, post speed, 50 miles per hour westbound, 40 miles per hour northbound, and 50 miles per hour southbound. And with that, we're done with the first part of our example problem, which is modeling geometry and traffic volumes. Next, we'll proceed to modeling our controller settings. For the second part of this example, let's enter our controller settings. And you have here on the slide set and in your problem statement all the inputs that are required. Let's get back to our HCS file. And let's start by modeling our phasing sequence. One way of doing this kind of modeling, you can click the movements on the phasing diagram and you can add or remove them. But you can also do that through the phasing wizard. If you click the phasing wizard button, you have to select a couple of questions here to answer. For example, do I have a protected left turn phase? And yes, I have all protected left turns. So phases 1, 5, 3, and 7. So let's keep all of them checked. The second question, do I have any permitted left turns? And here, my only permitted left turn will be the northbound left, so I want to uncheck the other movements. Do I have any right turn overlaps? And here I have one overlap phase, which will be the northbound right, which occurs concurrently with the eastbound left movement. And you can see that updated in the phasing sequence. And I don't have any lagging left turn phases. So with that, I'm done with this step. Let's close the phasing wizard, and you will notice my phasing sequence has been updated here. Let's also change our cycle length to 140 seconds. We have side street split phasing, which was already selected automatically due to the presence of this shared through left turn lane. And then let's proceed to our phase splits. So let's enter numbers as we have in our problem statement. You don't have to worry about the major street movements, eastbound through, westbound through. They are disabled because of the nature of this actuated coordinated control method. But once you start adding all the other splits, you'll notice the major street through splits, they are automatically updated. And once you enter all of them, they should match what we have in your spreadsheet. For the intersection, we have 4 seconds of yellow change for all movements, and we have 2 seconds of red clearance for all movements. Minimum green, I have 7 seconds for every approach, except major through movements, which are 20 seconds. So 7 and 20 seconds for westbound through, and then 7 for all the others. My passage time, 3 seconds for eastbound, westbound approaches, and 2 for the others. And here passage time is disabled for the major street through movements, again, because of the nature of the actuated control operation. We have recall off for every single movement. No dual entry, so let's uncheck all dual entry inputs. And we have simultaneous gap for both directions, east-west and north-south. And with that, we are done with our next step, which was modeling signal controller inputs. We're done with our data input process. What you can do next is you can go to our report and we can check what's going on in here. Just in case you're not seeing the report on the right side of your screen, that's something you can change by going to the view menu, reports, and you may either select right or bottom. So in my case, I see it on the right side of my screen. What the report will typically show us, you'll see a summary of the intersection movements, the lane configurations, traffic volumes. For the timer results, these are intermediate calculations that are primarily used to compute the average phase duration. And right here at the bottom, that's where I have my performance measures for my intersection. What's important for us to check especially volume to capacity ratio, or X. I want to make sure none of these exceeds 1, otherwise we would have oversaturated conditions and consequently a level of service F. I may also want to check the Q storage ratio. Anything that exceeds 1, you'll also see that this will cause queue spillover. So queues are backing up upstream of the stop bar, and they may cause blockage to any upstream intersections. And here we have a problem with southbound through movements. So maybe that's something that we may want to consider revising when we want to change our traffic signal controller operations. We have our control delay listed here. So this is my service measure. And based on these control delays that I have obtained, I have my level of service assigned for each one of my movements in the intersection. And these delays and level of service can also be aggregated for each approach. They are listed over here. And overall, my intersection here is getting an average control delay of 33.7 seconds per vehicle, which will be consistent with a level of service C. And that concludes our example and how we use HCS to model signalized intersection.